Welcome to the presentation of the paper on LZ77 factorization in sublinear time. My name is Dominik Kempa, and this is joint work with Tomasz Kociumaka. We begin by defining the LZ77 factorization. A longest previous factor, or LPF, at position I is the longest substring that starts at position I and has another occurrence earlier in the string, that is, at some position j smaller than I. In the example string, the LPF at position I has length equal to 4. The LZ77 factorization is then defined as follows. Given a string t of length n, we greedily, from left to right, partition t into LPFs, or single symbols if the LPF length is 0, and output the encoding of each LPF as a pair of integers containing its length and the position of an earlier occurrence. The number of pairs resulting from encoding text t is denoted as z of t. In the example, the LPF at position 12 is equal to 3 and has an earlier occurrence at position 7. We thus output its encoding as a pair 3, 7. The next LPF is similarly encoded as a pair 5, 5. Note that given this sequence of pairs, we can restore the original text t. The elements of this factorization are called phrases. The earlier occurrence of a phrase is called its source. In this variant of LZ77, we allow the phrase to overlap its source. A variant where this is not allowed is called the non-overlapping LZ77. Since all results in our paper hold for both the overlapping and non-overlapping variants, for the rest of the talk we assume the version allowing overlaps. LZ77 factorization has numerous applications. It is the most commonly used lossless compression algorithm. In the large text compression benchmark, it is the main algorithm used by over a quarter of all compressors. The list of file formats using LZ77 includes popular types like PNG, PDF, and zip. LZ77 compression is also used in virtually all modern web browsers and servers. LZ77 factorization is also a very well-studied measure of repetitiveness. Up to logarithmic factors, it is known to be equivalent to several other compression methods, including grammars, LZend, run-length Purus-Wheeler transform, and several others. Importantly, although many of the above methods are NP-hard to optimize, LZ77 can be computed in polynomial time. LZ77 is also the basis of numerous compressed indexes, which are data structures capable of storing the string in compressed form while simultaneously supporting queries on the original uncompressed sequence. LZ77-based indexes are known to support all of the most popular queries. Finally, LZ77 factorization is the main tool used in numerous algorithms to detect various regularities in strings. This includes exact and approximate repetitions, repeats with a fixed gap, runs, and several others. Efficient LZ77 factorization is one of the most widely studied problems, and solutions are known in all major computational models, including RAM, external memory, parallel, GPU, and quantum models. In this paper, we address the problem of efficient LZ77 factorization in the RAM model, and we assume that the symbols of the input text are numbers in the polynomial range with respect to the string length. This is the most studied variant of the problem, and it corresponds to most practical uses. Note that in such model, the input text can be stored in n log sigma bits or n over log base sigma of n machine words. To achieve this, we pack log base sigma of n symbols of text into each machine word. Since Lempel-Ziv proved that the number of phrases z is asymptotically bounded by n over log base sigma of n, it follows that, at least theoretically, in the RAM model, the LZ77 factorization algorithm running in O of n over log base sigma of n time is hypothetically possible. The first algorithm for efficient LZ77 factorization was proposed in 1981. It is based on suffix trees and runs in O of n log sigma time. Several years later, the dependency on sigma was removed. After reaching O of n time, the next barrier to overcome was reducing the space usage. Numerous algorithms managed to achieve the optimal space usage of n over log base sigma of n machine words, gradually bringing the runtime closer to linear. This was achieved in 2016 using a randomized algorithm, and a year later using a deterministic method. The main question we ask in our paper is whether the linear time bound can be further improved, while keeping the space usage optimal. We answer this question positively and present the first algorithm that achieves little o of n time. For example, in the most fundamental case of binary alphabet, our new algorithm uses optimal space and runs in n over square root of log n time. This is the first algorithm to break the linear time bound for this problem in nearly 50 years since the development of LZ77 compression. We achieve our sublinear LZ77 factorization as a simple corollary of a more general result that we develop in our paper. Specifically, we develop an index that admits sublinear construction and lets us quickly find leftmost occurrences of substrings in the text. More precisely, we show that for every text t and every constant parameter epsilon, there exists a data structure of size O of n divided by log base sigma of n that can be constructed in sublinear time and optimal space, and given any position j and length L, in O of log to epsilon of n time computes the leftmost occurrence of a substring of t from j to j plus L. Our index also works for explicit patterns. Given any length m pattern p occurring in the text, we can find its leftmost occurrence in the text with only O of log to epsilon of n overhead over the time necessary to read the pattern. Observe that using this index, we can easily compute the LZ77 factorization. Specifically, to compute the length of the phrase starting at position j, we binary search for the largest L such that the substring of t from j to j plus L has an earlier occurrence. Using the above index, computing L takes O of log of L times log to epsilon of n time. The total time to compute all phrases is minimized when all phrases are of equal length, that is, n over z. Thus, we can bound the runtime of this algorithm by O of z times log of n over z times log to epsilon of n. Applying the earlier bound on the number of phrases z, we thus obtain that by setting epsilon smaller than half, the computation of all phrases takes at most O of n times square root of log n divided by log base sigma of n time, which is also the time to construct the above index for leftmost occurrences. Thus, the factorization time is dominated by the time to build the index. We have thus showed that using the above index, we can compute the LZ77 factorization in sublinear time for small alphabet sizes. To develop our index for leftmost occurrences, we introduce and study a new type of query we call suffix range minimum query, or simply suffix RMQ. Recall that the classical problem of RMQ asks to preprocess an array of integers such that given any pair of indices BE, we can find the smallest value in the range from B to E. Here we assume that rather than returning the smallest value in the specified range, we instead return its position. In the example, the smallest value in the range is 2 and it occurs at position 7. The suffix RMQ query generalizes RMQ in the following sense. As input, in addition to the array of integers A, we are given an array of strings W, where each string is of length L. At query time, in addition to the indices BE, we are also given a string X of length at most L. The query then returns the position of the smallest value in the specified range, for which the corresponding string in the array W has X as a suffix. In the example, we search for a minimum in the range from 4 to 14, and the string X is 0, 1, 0. This means that we are interested in the smallest value among the 3 marked positions in A. In this example, it is 4, and hence the query returns its position 12. In our paper, we develop an efficient data structure for suffix RMQ queries. More specifically, we show that assuming that sigma to L is at most m, there exists a data structure that for the input arrays of size m occupies O of m space, answers suffix RMQ queries in O of log to epsilon of m time, and can be constructed in O of m times square root of log m time using O of m working space. Another tool that we use in our index is the technique of string synchronizing sets. Consider a text t of length n and a parameter tau between 1 and n over 2. We say that a subset of positions s in the text is a tau synchronizing set if it satisfies the so-called consistency and density conditions. The consistency condition requires that for any two positions that share a right context of length 2 tau, they are either both in S or both outside S. The density condition requires that in every window of tau consecutive positions, there is at least one position in S if and only if the position at the beginning of the window is not in a highly periodic substring. In our paper, we present a general construction of the index for finding leftmost occurrences that allows periodic substrings. However, for simplicity, in the rest of this talk, we assume that the input text does not have highly periodic substrings, in which case the density condition for string synchronizing sets reduces to simply requiring that every window of tau consecutive positions contains at least one position in S. It is known that a tau synchronizing set of size O of n over tau can be computed in linear time. When tau is sufficiently small, an even faster method exists that runs in O of n over tau time. We are now ready to give an overview of the components of our index. To illustrate some concepts, on the right we visualize the suffix array of the input text, which is simply a list of all suffixes of the text in lexicographical order, and each suffix is encoded using its starting position. Our index for finding leftmost occurrences consists of the following components. First, we store a tau synchronizing set S of the input text with the parameter tau set to some constant times log base sigma of n. Second, we store the set of the so-called distinguishing prefixes of all positions, which for a position j in the input text is defined as a substring from j to j prime plus 2 tau, where j prime is the successor of j in S. The set of distinguishing prefixes is visualized on the right. The third component of the index is an array A, storing the subsequence of suffix array containing all positions in the synchronizing set S. The next component is an array W containing the left context of length tau for every position in the array A. Next, we store the data structure supporting suffix RMQ queries on the arrays A and W. And finally, we store a trie of all suffixes of T starting at positions in S. Using our index, we compute leftmost occurrences of patterns as follows. Let P be an example pattern equal to 0, 1, 0, 1, 0, 0. The first step of the query is to compute a non-negative integer delta such that P from 1 to delta plus 2 tau is one of the distinguishing prefixes. Using delta, we then define a decomposition of P into two strings x and y such that length of x is delta. In our example, x is equal to 0 and y is equal to 1, 0, 1, 0, 0. Next, using the trie, we compute indices BE such that A from B to E contains all indexes S from our synchronizing set, for which the corresponding suffixes have y as a prefix. The range for y in our example is marked in blue. In the third step, we issue a suffix RMQ query on A and W with B, E, and X as arguments. In the example below, we highlight all strings in W that have X as a suffix. Among all such strings, only two are in the range BE. The prefix RMQ returns the position of the smallest of these two values, which in this case occurs at index 6. Finally, we retrieve the value at this index from array A, subtract delta from it, and return as the answer. The final value returned by the query algorithm is 10, and it is easy to check that it is indeed the leftmost occurrence of the example pattern. In the paper, we describe our index in a more general form by presenting a black box reduction from the problem of computing leftmost occurrences to suffix RMQ queries. More precisely, assume that we have a data structure that, given a sequence of k integers and k length L strings over integer alphabet of size sigma, answers suffix RMQ queries in time q, uses space s, and can be constructed in time p sub t using working space p sub s. Then, for every text t of length n over the same alphabet as above, there exist sufficiently small parameters k and l, and a data structure of size O of n over log base sigma of n plus s, where s is parameterized by k, l, and sigma as above, that can be constructed in O of n over log base sigma of n plus p sub t time using O of n over log base sigma of n plus p sub s working space, and computes leftmost occurrences of both internal and external patterns in time that depends on q and only has an additional log n term. This black box reduction implies that the complexity of finding leftmost occurrences is almost entirely dominated in all aspects by suffix RMQ queries, and that any new trade-off for the suffix RMQ problem immediately implies a new index for leftmost occurrences. Recall that earlier we demonstrated that using our index for leftmost occurrences, we can compute the length of the longest previous factor starting at any position in O of log L times log to epsilon of n time, where L is the length of the previous factor. In the paper, we show that with additional preprocessing, this approach can be improved so that the time for querying any LPF length is O of log to epsilon of n. More formally, we show that for any text t over integer alphabet of size sigma and any constant parameter epsilon, in time that is sublinear for small sigma and using optimal working space, we can construct an index of optimal size that can query any LPF value in O of log to epsilon of n time. To sum up, here are the main contributions of our paper. First, we presented the first sublinear LZ77 factorization algorithm in nearly 50 years since the discovery of LZ77. We obtained this algorithm as a simple application of a more general result that describes how in sublinear time construct an index for finding leftmost occurrences. For this new index, we first developed a specific trade-off that yields O of log to epsilon of n query time, and then proved a more general black box reduction to the problem of suffix RMQ. As an additional result, we also show how to further preprocess the index for leftmost occurrences to obtain an efficient index for querying LPF values. Example future questions include studying other trade-offs for suffix RMQ queries, eliminating the log n term in the query time of our reduction, and improvements to other variants of Lempel-Ziv compression. Thank you for listening to this talk.